So we're going to talk about bases now. The strong bases include the metal hydroxides. So M is just a generic metal here, either M+1, M+2, or M+3. So the first one here could be sodium, potassium, or lithium hydroxide, for example, the alkali metals. The second one could be something like calcium, magnesium, barium, zinc hydroxide, +2 metals. And then this third set would be something like aluminum, iron 3, chromium 3, something like that. Metal hydroxides, when you dissolve them in water, they form the metal and they form hydroxide ion. These are strong bases, which means that whatever concentration of sodium hydroxide, for example, you started with, it will dissociate into, so let's say you start with 1 molar sodium hydroxide, that will dissociate completely into 1 molar sodium ion and 1 molar hydroxide ion. If you have 1 molar calcium hydroxide, that will dissociate into 1 molar calcium ion and 2 molar hydroxide ion, because it's 2 hydroxides formed for every 1 mole of the metal hydroxide. So these are our metal hydroxides. You'll notice that there are +1 metals like sodium, lithium, potassium hydroxide listed first. The second one listed there would be a divalent cation like calcium, magnesium, so a +2 ion. And then the third one there would be a +3 ion like aluminum or iron 3, right? So any of the metal hydroxides would serve as strong bases. The +3 cations have other issues associated with them. You're not going to see examples of those. I'm not going to give you examples of those. And we'll talk about why at the very end of the chapter. It's something that you haven't learned yet. So again, here is our table of electrolyte classification from chapter 7. And so you'll notice at the bottom is sodium hydroxide and potassium hydroxide. And at the very bottom, it lists other soluble ionic compounds. The solubility is the issue of why it doesn't list more hydroxides there. So it only lists the group 1A hydroxides because they're the ones that are soluble. Remember in Chem 101, you learned solubility rules that stated that the alkali metals form soluble salts. And the problem with hydroxides is that if it's something like calcium hydroxide or barium hydroxide or magnesium hydroxide, those tend to have limited solubility in water, which is why they're not listed here as strong electrolytes. However, I think we're conflicting the ideas of solubility and dissociation. They are not really the same thing. And so I'm going to put this statement up here that says many hydroxides just have low solubility. But whatever dissolves definitely dissociates and ionizes. And so when I give you calculations on a quiz or as a practice or as a homework or on a test, I might give you magnesium hydroxide or calcium hydroxide. And you're just supposed to assume that whatever I give you is dissolved completely. Okay, so if it fully dissolves, it definitely fully dissociates, right? 100% all the way to the right. Now, weak bases only partially dissociate, and we're going to learn the different kinds of weak bases. There are generally two sort of categories of weak bases, which we'll learn about. But in general, a base will accept a hydrogen ion, and if you're dissolving it in water, it accepts the hydrogen ion from water, and it forms its conjugate acid, BH+, and it leaves water as water's conjugate base, which is hydroxide. And so the hydroxide that forms when water gives away its hydrogen ion, that is the reason why these are bases. So now we're going to talk about weak bases. Here we have our reaction equation. Weak bases only partially dissociate, and therefore that is why you have a double arrow here, just like for the weak acids. So in this case, the base will abstract a hydrogen ion from water. The proton will be transferred from water, which is the acid in this case, to B, our generic base, and that will form the conjugate acid of the base, which is BH+, and the conjugate base of water, which is hydroxide. Now, here we're going to look at an example. Ammonia is definitely the most common weak base that we are going to learn about. But we're going to learn that ammonia is one of a family of compounds called amines, and all of the amines would serve as weak bases, and we'll talk about that when we get to that section. So here you see ammonia is the base, and it's going to take a hydrogen ion from water, and it's going to form its conjugate acid, which is ammonium ion, and it's going to leave water as hydroxide. So those are the models that go with those. Ammonia lies far to the left. It has a Kb that tells you it's about 1.8 times 10 to the minus 5. Yeah, 1.8 times 10 to the minus 5. And so essentially it's about 1% dissociated, 1% ionized. And then 99% would stay on the left-hand side. And so this equilibrium lies far to the left. The degree of basicity, how strong a base is going to be described by its Kb. Okay, so large Kb values are going to lie further to the right. Those would be considered stronger bases because they're going to form more hydroxide ion in solution. So base strength is related to Kb. This is a table that you will have on future quizzes and exams that lists all the Kb values. Ammonia is at the very top. These are all listed alphabetically, and these are all compounds that sound awfully strange and they look awfully strange, and we're going to talk about these. These are all examples of what are called amines, and they're all in the same family as ammonia, so you're really going to treat them all like ammonia. Okay, we'll talk about how much they look like ammonia on a future video that's going to in some way have the word amine in the title. Now, weak bases will either be amines, like you see on the left here, or at the end of this section, we're going to learn that weak bases might also be the conjugate bases of weak acids, and we will learn that at the very end of this chapter. We'll come back to that.